Okay, we can start.
We can start?
Yes.
Okay. So, hello. Welcome to the control center of the ALICE experiment at CERN. Here we are on Researchers' Night, ready to show you the control room and tell us about our experiment. But first, let me introduce the people who are connected interactively. There is the University of Malta. Can you hear us, Malta?
Hi, yes, we can hear you. Hello.
Okay, good. And there is also the Vienna with two institutes, Practical Robotics Institute and the Stefan Meyer Institute of Subatomic Physics. Hello, can you hear us from Vienna?
Yes, we can hear you. Can you hear us?
Good, yes. Okay, so I am Despina Hadjifotiadou. I am an experimental physicist working at the ALICE experiment since 15, 16 years. I'm Greek, but I'm employed by Italy, so I work for the National Institute of Nuclear Physics, what is called INFN in Bologna, but I am based at CERN. And I work for one of the projects, one of the ALICE detectors, which is called ALICE Time of Flight. And I'm also the outreach coordinator of the experiment. And here is my colleague and friend, Giacinto.
Yes, good evening to everybody. Welcome here in the ALICE control room. My name is Giacinto De Cataldo. I'm an Italian physicist of the Italian National Institute of Nuclear Physics. I'm in ALICE since 2000, and I'm leading a couple of projects. One is a rich counter for the particle identification, which let us to identify particles once they are produced in the collisions. And the other project is called LHC interface. It's a project that lets Alice to operate in a coordinate way with the LHC, because of there are some injections that has to be coordinated also with the experiment.
So let us first tell you some things about our experiment, and then you can have a virtual tour of the control room, and we'll tell you what's happening here, and of course you can ask questions. This is the idea, so get ready. So for those of you who haven't had an introduction, or for those who are joining the webcast just now, what you see here is an aerial photograph of CERN. CERN is the small triangle, and the various circles are the accelerators. CERN, as you must know, is the laboratory for particle physics, and it provides the beams needed for the experiments which study the fundamental particles, the elementary constituents of matter. So CERN has a whole chain of accelerators. And what you see here, I'm not sure if you see the small one is called PS, proton synchrotron. The next one is called the SPS, super proton synchrotron. And the big circle, this is the LHC, the Large Hadron Collider, in a tunnel of 27 kilometers circumference, 100 meters below ground. In this accelerator, two beams of protons or lead ions circulate in opposite directions and collide at 4 points where there are 4 experiments. And these are, you see their names, Atlas, CMS, Alice, and LHCb. And right now we are at the Alice experiment. So here, this is again an aerial photograph taken from Google Maps of the installations of Alice. Where we are is point 2 of LHC. The experiment is of course underground, but here there's a number of buildings, and I'm not sure if you can see the cursor. The building where we are is the one with a small post, a big poster in front. The experiment is 56 meters before ground, and we in the control room are of course on the surface. And here you see a photograph. Oh, sorry.
We closed
Here you see a photograph of the Alice experiment. This is to get an idea of its dimensions. This is 16 meters tall, 16 meters wide, and 26 meters long. If you take the height into account, one could say it's something like a 5-story building. It weighs 10,000 tons, the equivalent of the Eiffel Tower in Paris. And what you see is a big solenoid magnet. Well, the red structure is the iron of the magnet. And inside this, there are layers of detectors which see the particles produced from the collisions. So Alice, as you see on top, stands for a Large Ion Collider Experiment. It has this name because it is designed to study collisions of ions, more concretely heavy ions, and even more specifically lead ions, bare lead nuclei. Now, why do we do this? We do this because by colliding these lead nuclei, we recreate a state of matter that we believe existed in the very early universe, where the normal constituents of matter, which are quarks in principle and electrons, were free in a kind of soup called quark-gluon plasma. Now, this was possible can you stop sharing? Displaying. This was possible under the conditions of extreme temperature and density that existed at the time, some fractions of a second after the Big Bang. And what we do in Alice is that by colliding these lead nuclei that have a very high energy. If we talk about velocity, they travel almost at the speed of light. So at the point of collision, we have very, very high temperature, trillions of degrees Kelvin, and very high density. So for a very brief time, we recreate a droplet of this primordial matter. And what we want to do is to study it so that we can understand the properties of the universe at its very beginning. Let me just try to show a video that gives an impression of this. Can you share? Yes. Okay, I'll start it again.
You can describe here what actually you have already seen.
Yes, okay, yes. To you?
Well, we will see now in a few seconds again a couple of disks which represents the lead nuclei approaching in the opposite direction. They have been accelerated by the LHC, of course, and once they collide, you will see again a certain number of small colored sphere appearing, and they will be the evidence in this animation that the quarks and gluons are made free, so not any longer confined in proton and neutrons, and then freely to interact.
Okay, so I propose that we now pass to the virtual tour of the control room.
Yes.
And
okay.
Please don't forget to think of questions to ask afterwards.
Yes.
So
we are moving now, as you can see, we are moving now in a short description of the screen you will see on the now broadcasted. These screens, of course, are connected to the main online systems in ALICE, which are needed to operate the experiment during the data taking when LHC is delivering collisions. What you see here are the two main display. The left one, as you see, is the so-called event display, where we have at one glance the idea how the experiment is working. If we do not see events there, of course, problems are in with the data taking, for example. On the right side, the screen is of the so-called experiment control system. It's from the hierarchical point of view, it's the highest in this hierarchy, and from there we can stop the data taking and start the data taking. Create the so-called partitions where different detectors are put together, and at the same time the experiment can take data for different physics subjects. So let's move then now to the other screens. Now on the right you see again two other screens. The rightmost, which is the white one, is of trigger. What the trigger is in an experiment. As you have been told, there are collisions. LHC, it's able to provide collisions, lead or protons, from few kilohertz, means few thousand of collisions per second, up to 100 millions of collisions per second, in this case proton-proton in the high luminosity. So the trigger gives electrical signals to say we have had a good collision, so we should take data. And these triggers, this signal, are then fan out to all the detectors in ALICE. ALICE is integrate 18 different detectors. So this signal then is sent to the detectors, and we start the event acquisition. This, as I said, can go from 10 kilohertz in lead up to 100 kilohertz in proton-proton. On the left side of these two screens, you see the one which is broadcasted by LHC. And then on the top part of the screen, of the display, you see proton physics set up, means that the machine is in the mode proton physics, and set up means they are preparing now for the next injection. LHC will be filled up with train of protons and then accelerated. So these information are relevant, and we will see in a while, for the run coordinator, which will, of course, take decision when and how to run the experiment. Let's move on now on the new display. These sets of 3 displays integrate the previous information. You see on the leftmost side, there is this white display presenting the data quality monitoring. While taking data on each trigger, we want to be sure that the detector is not actually out of order. And then the different sub-detectors are monitored. As you can see, there are a swapping of the images on. The sub-detectors can then are checked on the data they are providing if this data respect a certain level of quality. This monitoring is absolutely important in order to prevent that corrupted data are saved and stored on the mass storage devices. In the middle, you see then the detector control system, the display, which, if we can make a parallel with a space station, would be the place where we check that the engines are there, ready to start, and there actually we check that the temperature, the voltages, pressure, and everything to run the different detectors are okay. And then the rightmost is the display of the ALICE LHC interface project, where all the information from ALICE are monitored and sent to LHC and vice versa, such the two complexes are operated coherently. In fact, ALICE as LHCb is located in one of the injection line, means on a place where the beams are injected in LHC. These actions, this operation, of course, can intrinsically have some risks, and for that we protect the detector, we maintain the detector in off position until LHC is filled in, and then accelerated, the particles are accelerated. Once this is completed, the experiment in stable beams here is then put ready to take data. So all these subsystems, as I said, are coordinated by the experiment control system, which is under the control of our colleague, as I said, the run coordinator, that I would like to call him here, please. So, good evening. Could you introduce yourself and present your role in the experiment, please?
Yes, the camera.
Yes. Then let's move. This is the experiment control system.
Yes, but first I want to introduce myself. My name is Benjamin Dönigus. I'm from the University of Frankfurt in Germany, and I'm currently the run manager of ALICE. And my task is to provide information for the shifters, for the people working here, how they should do their work. Doesn't matter. Yes, like this. Okay, and yes. I think that's all from my side, but we should explain what the people are doing here. For instance, we have the ECS shifter there sitting, and he's basically checking starting and stopping runs. He's checking the busy times of the detector and also looking about the data rates, checking the event rates, and about the HLT. I don't know if Giorgio did not tell anything about the HLT. We have a different level of triggers, and the highest level is the high level trigger, and the short form is HLT. And we use this to decide at the end if the event was good or not. And we also do this the event reconstruction in between for the TPC. So we do clusterization on this huge computer farm, which is called HLT, high level trigger. And the second, if you move now to the DCS shifter, so his main task is to monitor each detector, all detectors we have, and especially the voltages, for instance, the temperatures of the detector, and also check if everything's working nicely to take data. And the last person I want to mention here is the shifter for the data quality monitoring. He's looking all the time for each detector if the quality of each detector is fine. This is his main task. And all shifters are here 8 hours for each shift. And we have 3 shifts in total per day. So we have 24 hours of data taking. So
Please, what about the organization of shift, as you said already, and everything is every time filled in? Is there particular difficulties for you to organize this attend of the shift by the shifter?
So the shift is in principle done through all institutes of Alice, and problematic it's mainly when people get ill. For instance, we had this case last week. Someone went ill, which can happen, and the person has the right to get ill, and we have to organize a backup very quickly, and this is difficult in some sense.
Thank you very much. Thank you very much for your contribution. And then we are back here. Actually, we have more or less introduced the basic elements of our experiment, and we are ready for the questions. So I would then leave you to ask, and feel free to come with any kind of question regarding our experiment and our scientific activity.
Hi, I'm calling from Austria. I have one question because we are working on very practical issues in our institute. My question is, like, you have very interesting experiment, and you will have some kind of findings. Where you can apply this finding, implications of what you concluded in your experiment. Is there any kind of practical applications or issues?
Well, I'm not sure we have got the full questions because we had some cuts during your questions. I mean, while you were asking questions, but if you say the medical application in general of physics, if I've well understood, that's of course something which is also beyond what is.
That's what I'm asking. Yeah.
Very good. So I would say that we have really many evidence where the physics is providing a lot of useful, I would say, theoretical framework and practical tools to the medicine. For example, the hydrotherapy. We use all the technique of the accelerator technique in the medical field because of the size of a beam is of the order of the cross section of a size of a beam is of the order of tens of microns, or let's say 100 micron, and the capability to drive the beam over some, for example, cancer or other place where the surgical cannot really intervene. Then the physics is providing tools able to arrive there, for example, in the brain intervention where the surgery intervention could not do. But let me add something more, I would say, evident. Of course, the X-ray radiography, I mean, this is a bit of history, the RNM. So we have really a huge number of evidence where the physics has provided tools, as I said, and also theoretical framework where the medicine, of course, has got a lot of benefits. Last but not least, we use the GPS. Yes, it is not medicine, but I would like to remind you that GPS is based on a battery of satellite, geostationary satellite, which uses the general relativity to correct the time the time difference between clocks which are running on the satellites and on the Earth. If we didn't have, we didn't have the general relativity for this correction, we would have ignored the existence of the fact that the time is not absolute. So you see, from the relativity to the GPS, it seems something that maybe, yes, few people maybe knows, but it's absolutely fundamental for this very important tool humanity today can have. I do not know if Despina has something else to add on that, and I hope I've given an answer.
I think
to
we've
your question.
covered the spectrum more or less. Did we talk about the World Wide Web?
Not yet.
This is one of the spin-offs that is really known worldwide, and this is something that exists since 27 years. It exists since 89, right?
Yes, it is. It was the first time I used via.
So it is mainly, to conclude this, it is mainly all the technology which is developed to do the research that we do that finds many, many applications. The actual physics results, for the moment, this is just adds to our knowledge. If some applications will be found later on in the coming decades or centuries, who knows? More questions?
Michael, we cannot hear you any longer. Michael, can you hear me? We
Yeah,
cannot hear you.
sure. I just muted the microphone. I mean, if we still are allowed to ask questions, before we had a question here in the room, how many, I mean, often this, first of all, how many particles are in the accelerator? And then how often do they collide?
Okay. Would you me or would you answer? So, as I've been said, we have two beams circulating in opposite direction. Each beam has an intensity of the order, and we could see on one of the screen over there, it was before, of the order 10 to the 14, means that 10 to the 14 protons. Now, these have to be split in 2,000 bunches. So in each bunch, we have about 1,000 billions of protons. And we have 2,000 bunches in one beam and 2,000 bunches in the other. Of all these bunches, some of them collides in ALICE, some of them collides in CMS and ATLAS, and some of them collides in LHCb. So according to the number of these colliding bunches, the luminosity, which is the number of collisions per second, depends on how close the beams are set, how do they intersect. And the number of collisions per second, as I said, can range from, let's say, 8 kilohertz, means 8,000 collisions per second, up to some millions, or sorry, even more, tens and 100 million of collisions per second when we are colliding 2,000 bunches in CMS or ATLAS. And these are per second, so 100 millions of collisions per second in proton-proton.
Okay, thank you. I'm asking if there are more questions.
I just have one more question. How much energy do you need to speed up a proton? And can you make an example? What it for normal people?
Yes. So I don't know if you want to say something.
Well, the energy is to which we accelerate it is at the moment 6.5 tera electron volts, which is equivalent to
a TGV, which is a train grande vitesse en français, launched at about 150 kilometers per hour. So the energy which is stocked in one of the beam is equivalent to a train, train with a high velocity at about 150 kilometers per hour. So, or even the equivalence can be established with an airplane flying at 800 kilometers per hour. I'm speaking a jumbo. So this is the amount of energy which is stocked in one of the beam. Now, how much energy do we need to make LHC running? What is the energy we have to ask to EDF, which is the Électricité de France, or to the Swiss electrical network? Well, it's the equivalent of a city like Geneva, which is 300,000 people. So it's not a negligible amount of energy. But of course, we need 160 megawatt per hour. So it's not, of course, something negligible. However, there are some periods in the year where Here at CERN, we limited the activities. And of course, this is coordinated with the two countries providing the power to LHC or to the full installation at CERN. I hope we have given figures which are answering in the question.
Any questions from Malta? Sorry, if you wanted more, go ahead.
No, I just wanted to say thanks. So perhaps we give to Malta or some first.
Yes,
and then
of course. Yes, come on, Malta.
Yes, so we have a question.
I was just wondering what is the point of data generated for each experiment? I mean, how long it takes to analyze it?
Did you hear the question?
I'm sorry, no, I couldn't. So the microphone maybe was muted, Gianluca. Please.
The question was how much volume, what's the volume of data generated by this experiment, and how much time does it take to analyze it?
How many petabytes had we recorded?
Well, we have some. I mean, we are of the order, at least now, before the high luminosity, we should be at level of several petabyte, terabyte. And so for we have of course, here at CERN, some center where these data are stored and the time for the analysis. This is a question that needs a bit more, I mean, some, I would say, clarification around. In order to analyze such complex events each experiment is providing, actually you need thousands and thousands of CPU. Means thousands and thousands of computers that at the same time have to cooperate in order to analyze the events. This is carried out via the so-called grid, which actually interconnect several countries and several thousand of computers. So the task is then split in the different countries, the events are analyzed and then put together. As you have seen, the 2012, we got the the evidence of the existence of the Higgs bosons. And it took about 1 year and a half of that analysis. So in principle, when you take data for 1 year, more or less it takes an equivalent amount of time to complete the full analysis. And of course, depends on how complex the analysis is, depends on which physics channel you want to analyze. So as I said then, we need, first of all, the grid infrastructure, which is a sort of, as you said, distributed computing facility, distributed all over the world. And at the same time, you need, of course, about several months to analyze the data taking during 1 year. Despina, do you have other comments? Or
just to say that is to go a little bit in the beginning of the whole process. The data we take, what we call raw data, which are the numbers we record from our detectors. These are, you can think of them like photographs, okay, from a 15 million pixel camera. The first step of the analysis is what we call reconstruction, which we can imagine as a kind of translation of this data to something more concrete, something where these numbers correspond to the physical quantities they represent, like position of the particles, energy of the particles, what else, time it took them to travel, all this. To do this, we need a lot of parameters from the detectors. We need to do what we call calibration and so on. So already this first step of the reconstruction of the data is something that takes a lot of time, a lot of CPU, and generates a lot of data, the reconstructed data, and then it's all the analysis that Giacinto talked about, the various physics channels and so on.
Other questions there?
Maybe a more general question, but do you have any advice for young people who are considering to study particle or experimental physics? I mean, is it an interesting time to be considering these studies?
Absolutely, yes, Despina.
By all means, if you are interested, do it. And, what will happen later on, who knows? At the moment, LHC is running it has been running for 6-7 years. It will run another at least 15 years, if not more. There are new projects in the pipeline. I don't know, maybe we can mention them. Since you asked, CERN is always, it has its running projects, but at the same time, it's looking into the future. So right now, there is something called CLIC, Compact Linear Collider, which, if it is ever made, will be a collider of electrons with positrons, a linear one. There is something that started relatively recently, which is not even a project, it's a study group called FCC. This stands for, what is FCC? Future Circular Collider, which will be something 4 times as big as the LHC in circumference, 100 kilometers, and 5-6 times the energy. It will reach maybe 80 or 100 TeV. I mean, nothing of this has been approved yet, but I want to say that we're looking into the future. There is future in this field. So if young people are interested, they should go for it. And maybe I don't know if they told you there during the evening, I don't know what activities you followed. CERN has many opportunities for young people, like starting from summer students, students from the 3rd year of their studies on. They can come to CERN for 2-3 months in the summer, work in an experiment, but also follow lectures. And this is a fantastic experience. What else? CERN also offers technical students to more applied, let's say, fields like engineering and applied physics, doctoral students, then fellows to people who have their PhD already. So there are many opportunities for young people.
Absolutely, yes. I would just add a few considerations. These are all the opportunities. Why I would then encourage, in addition, students to come and study physics and later to come at CERN. From my point of view, the universe is an open book. It's something that we have to investigate as a human being, where we can find, answer about our origin and maybe our destiny as well. So today, I'm sure you have already heard today, or lately, about the fact that the physics, when we look around or we look at the sky, we see just the 4% of the existing matter. And what about then the so-called dark matter? What about then the dark energy? So you see, these are questions that needs to get an answer. LHC experiments are trying and working hard on this. But of course, to add new idea or to add contribution to solve the problems the physics now is facing, like, for example, will we be able to provide a unified theory for all the interactions? I mean, the known interactions are 4, but 3 are organized in a well-known mathematical framework, which is the so-called standard model. But there is also the gravitation, which of course tell us the general relativity, how the universe is evolving. So how we can put all these things together? We need then young scientists with the good idea, with smart, and of course with a strong will to give a contribution and to be curious, because the curiosity is one of the main ingredients to be a physicist. So I encourage you to come and to go, and to register you at university as a student in physics, because this will let you to participate in this great adventure, which is the discovery of the universe and of the secrets of the nature.
Some more questions?
Yes, I'm Simon from Vienna, and I want to ask, how do you get the particles hover in the tunnel of CERN? Why don't they crash into walls?
I didn't understand how you get the particles, how they don't crash into the wall.
And how do you get hover the particles in the middle of the tunnel? Why don't they crash into the walls?
Well, you keep them in the exact trajectory. First, the particles move, circulate inside a beam pipe, which is where there is very high vacuum. We have removed all the air to avoid collisions of the beam particles with the air, which would then destroy the beam. Now, and of course, we have to keep them in the center of this beam pipe, not to touch the walls. This we do with magnets. In general, we make the particles do the trajectory that we want them to do with magnets. If we did not have magnets, the particles would go straight. They would travel straight, okay? But we have to force them to go around in this circle, which is the LHC. And for this reason, we have 1,232 magnets, which are 15 meters long each. These are actually double magnets, one for one beam and one for the other, but in the same external external metal cover. And we adjust the magnetic field in such a way, combined with the energy of the particles, that the particle stays exactly in the middle and does not touch the walls. Okay?
Okay, thanks.
You're welcome. Anything more? Anything else? There is a question from social media, which I can answer. The question is it possible to visit Alice? First, let me say that in general, CERN has a visit service which organizes many visits. I think by now we have something like 100,000 visitors every year, even more. In Alice, we have an exhibition which right now is in the process of being redone. So soon we will have a new visitor center, hopefully at the end of this year, beginning of the next year. So certainly we can arrange. At the moment, Alice is not in the official circuit of CERN visits, but I think it will soon be, starting from next year. So you can arrange, you can find on the web the site for CERN visits and request a visit and so on. And here you can also get an impression of the place, because it is where the exhibition and the control room are just next to the pit from where everything has gone down. So you can really get an idea of how everything went down to be installed. You can take photographs of the control room. Of course, you cannot come in. And let me just say the site is cern.ch/visits for CERN visits. So
we would like to thank, of course, the 140 people which are following this webcasting. We are really happy to know you are there. You are, of course, welcome to go on the website and reserve a visit for you. We will be happy to welcome you here. Of course, the visit down to the experiment is not, of course, allowed while LHC is running, of course, but you will see outside the old installation or the exhibition. And I would say then do not hesitate to ask for a visit, and we will be very happy to host you here.
Actually, you can also write directly to Alice Visits at cern.ch right now. Anyway, I think we have another 4 or 5 minutes. So are there more questions?
Yes, we have a question from Malta.
Yes.
The question is, I read in an article that a new particle that is outside the standard model had been found in recent experiments in CERN. Could you explain what this particle is, and are there any theories which prove the particle's existence?
Well, actually, Gianluca, I have to say that what has been confirmed is that that particle, which was the consequence of statistical fluctuation, is not any longer confirmed. It was a particle which was around 730 GeV, giga electron volts, but when we say statistical fluctuations, we mean that there are, in the number of the particle production during the LHC collisions, we do not have enough events to really establish if that what we see is just background or a real signal. It's a pity, but actually it is not any longer there. In any case, if it would have been there, if it was there, there were already several, of course, speculation on its, how to say, nature and how it would have been fit in the standard model. But these really are just speculation, so I would not say more on that since it has not been confirmed. Sorry.
Okay, thank you.
Any other question? From Vienna? Then I guess we can close at this point.
It has been a great pleasure.
Yes, thank you very much for your patience, for your interest.
And so...
yes, next visit is a CMS at 10 o'clock.
Tuned.
For those watching the webcast, 10 o'clock CMS, the compact muon solenoid. You go down?
Yes.
You will even have the possibility to go down virtually and see something 100 meters below ground.
So then let's stay tuned on this web emission and have a nice evening.
Okay.
Thank you very much.
Thank you very much, Vienna, Malta. Bye-bye.
Thank you. Bye-bye.
Bye to the people watching the webcast. Good night.
Bye-bye.